Hi, everyone. Welcome to our Life on Mars Commodore Classroom hosted by the Miami chapter. My name is Isabella Poschel. I'm a 2009 graduate of the College of Arts and Science, and I'm the Arts and Volunteering Chair for the Vanderbilt Alumni Miami chapter. I'm here with Alumni Relations staff members, Catherine Hooper and Caroline Johnstone. To start, I want to give you guys a quick update about the Miami chapter and the activities that we're putting on in the next couple of months before I introduce our speaker and guest of honor. On December 2nd, we have a virtual networking breakfast with the Tampa chapter. All industries are welcome. And the core program is also looking for volunteers. All the interviews will be virtual and they will begin in December. So if you're interested in volunteering prospective students, please sign up to be part of the core program. Also watch out for more Commodore Classroom lectures such as this one in 2021. The New York chapter will be hosting more lectures throughout the year, inviting your favorite professors to speak on a wide range of topics. A few more details about tonight's event. The chat box is open for questions, so please feel free to drop your questions there, and I will go ahead and read them for Professor Weintraub. And at the end of the discussion, any questions that he hasn't answered, we'll go ahead and pull from the chat box if time permits. Also, our alumni relations staff is going to post a quick 3-question survey in the chat box, so please complete the survey before you leave the meeting. And now I want to introduce our speaker, Professor of Astronomy, David Weintraub. Professor Weintraub is an expert in astrophysics who also writes about extraterrestrial life, human space travel, and space colonization. He is an award-winning teacher and researcher who has written four books, including Life on Mars, What We Know Before We Go. Please give a warm welcome to our speaker, Professor Weintraub.
Hello, everybody. It's nice to be here. I wish I were in Miami because we had a light frost the last 2 mornings and you've got a slightly better climate at the moment. As long as you don't have too many hurricanes. All right, what I want to do is start by sharing my screen with you. So this big face is going to go away and we will head to Mars in a moment. So here we go. A number of years ago, I became very interested in the question, is there life on Mars? Because I began to pay attention to what NASA had been doing for, at this point now, the last 3 decades since the early 1990s, which is focus on exploring and learning about Mars. And as an astronomer, I don't study the planets for the most part, though I did a little bit of work studying Pluto. But my work is on stars and how planets form around other stars. But nevertheless, my interest was caught by trying to know, wanting to know for myself, what's going on with all this exploration on Mars. So I spent a number of years learning about it. And once I knew enough, I decided that there was a story that ought to be told. People need to know what's going on with NASA's focus on exploring Mars. And the result was this book, Life on Mars, What to Know Before We Go. It was originally published in 2018. The paperback edition, the revised paperback edition, came out just a week ago, so I'm very excited about that. And it's been translated into a number of different languages, none of which I can read, except my name on the cover, but that's kind of exciting as well. So this has been a really fun project for me because there seems to be a great deal of interest in this. One of the reasons you should be extremely interested in the issue of Mars, not necessarily the book itself, is that there are 3 spacecraft headed to Mars. They were all launched in July. They will all arrive at Mars this February, and 2 of them will have landers that are focused on this question. The goal for those landers is to look for evidence of life on Mars. So let me move into the presentation. The first thing I want to do is ask you a few questions, and then I'm going to try to answer those questions. If I can figure out how to make my screen change. There we go. All right. So these are the big questions about Mars I think all of us should be asking. Can we go to Mars? And the associated question, when will we go to Mars? Does or did life exist on Mars? And then what I think is the most important, perhaps an existential question here, should we go to Mars? That's what I'll finish with. That's for the most part, that's what was added to the book, a last chapter, which is about the ethical and moral issues raised in that third question. So let's start here. Just this week, 4 astronauts were launched on the SpaceX Dragon capsule to go to the space station. A successful launch, a successful docking with the space station. This is the beginning of what I'll call the SpaceX age. Why is that a big deal? Besides getting more astronauts up and down to the space station, it's a big deal because Elon Musk created SpaceX because he wants to go to Mars. I don't know whether he wants to be the first person on Mars himself, but Elon Musk's goal with SpaceX was to build rockets that would be capable of taking humans to Mars and then colonizing Mars. And for the last 20 years or so, SpaceX has set goals for building new rockets, being able to successfully launch them, be able to recycle parts of the rockets. They have been 100% successful. They haven't met every deadline in their timeline for when they're going to launch a particular rocket, but they have been 100% successful in achieving their goals at some point. Elon Musk has said that he's worried that we are destroying this planet. That's kind of hard to argue with. And that because we're destroying this planet, humans need to colonize Mars so that once we destroy this planet, humanity still exists and has a chance to continue living on this other world. You can argue as to whether perhaps we should spend some time and money not destroying this world before we go and colonize Mars, but that's a whole different issue. Elon Musk is focused on going to Mars, and he has a good chance of getting there. He's not the only player in this game. Jeff Bezos, who you're all making wealthier with your Amazon purchases for Christmas this year, he has his own Blue Origin space company. If you have enough millions of dollars, apparently you can now have your own space company. The most recent launch of what he calls the New Shepard rocket was just a month ago. Jeff Bezos has a plan. The first part of the plan for his space company is to put what he calls 1 million people to work in Earth orbit. I don't know what those 1 million people are going to do in Earth orbit other than perhaps deliver packages for Amazon, but he plans to put them in space and put them to work, and then he wants to put a colony on the moon, and then he wants to go to Mars. Mars is not his first priority, but there's no doubt that Blue Origin, led by Jeff Bezos, is planning to send astronauts to Mars. There's another player in this game, that's the United Arab Emirates. In 2017, the UAE announced that they were going to build a space program, and by 2117, in 100 years, they would have a colony on Mars. This is a cartoon picture from the UAE space program of what they think their colony on Mars might look like. The UAE launched their first interplanetary spacecraft this last July. That's one of the spacecraft that's on the way to Mars. Last but not least, this is a cartoon illustration from NASA about their journey to Mars. The only thing you really need to know is that it is entitled Journey to Mars. The details don't matter. NASA also plans to head to Mars. So there are at least 4 players in this game of trying to colonize Mars. I will say that NASA's plan is just a little bit different because NASA is talking about sending astronauts to the Mars system, not actually sending astronauts to the surface of Mars, not actually building a colony on the surface of Mars, at least not yet. They are planning things for how we might extract water from Mars, how we might extract oxygen from Mars. But at the moment, NASA recognizes that in the fairly near future, we may in fact be able to get astronauts to Mars and land them safely on the surface of Mars, but we can't bring them home. SpaceX may be able to send astronauts to the surface of Mars and in fact build a colony on Mars. And maybe those astronauts will survive the 7-month journey to Mars. Maybe they will just survive the descent to the surface. Maybe they will find enough water and be able to grow their own food, just like Matt Damon did in his movie. but they can't get back off the surface. They're not coming home. For the foreseeable future, we do not know how to lift a rocket off the surface of Mars and bring all those astronauts home. So it's a one-way journey, and it might be a suicide mission, but we can get there. So here, we're back to the big questions we started with. Can we go to Mars? Not yet, but we will be able to go soon. When will we go to Mars? I would say by 2030. Within a decade, I think it's very likely we will have rockets capable of taking astronauts to the surface of Mars, and we probably will do that. Whether that's NASA or private enterprise that does that, we will have the capability of putting footprints on the surface of Mars within this decade. I don't think that is wild speculation. I think that's how quickly our rocketry, our engineering has developed. So in the lifetimes of most or all of us, we will see people land on Mars. That is just incredible. All right, let me tell you then a little bit about Mars, because if we're going to Mars, we should understand this place and understand what the fascination is for Mars itself. This is a composite image of Earth and Mars to show their approximate sizes. Mars is smaller than the Earth, but it is the most Earth-like planet in our solar system. How Earth-like is it? That's the question that really is confounding scientists right now. The first thing we learned about Mars in the telescope era, the telescope was invented in the early 17th century. The first thing we learned about Mars was an observation made by Christian Huygens, a Dutch astronomer. He watched Mars night after night, and he drew this sketch. This is before cameras, before iPhones. He actually took a pen and paper and drew a sketch of Mars. And this is his sketch. The patch he saw on Mars is still there. It's called Syrtis Major. We know exactly what he was looking at, this dark patch on Mars. He watched it, and he saw that Mars rotates. He measured the rotation period of Mars and discovered that it was 24 hours. There's another planet you're familiar with that has a rotation period of 24 hours. That rotation period measurement was improved over the next century, and by 1800, we knew that the rotation period was actually 24 hours and 39 minutes, but that's awfully close to one Earth day. We knew that the orbital period of Mars is 687 Earth days, so not quite 2 Earth years. We had learned by 1800 that Mars has polar caps, that Mars has seasons, that Mars has a very thin atmosphere, like the Earth, that Mars has clouds, and that Mars has a solid surface. By 1800, we knew that Mars was very much like the Earth, more so than any other planet in the solar system. And as a result, astronomers focused their attention on Mars. Over the next 100 years, astronomers invented a lot of ideas about Mars which were almost entirely wrong. They were convinced that Mars was like the Earth, so they saw things that weren't there that proved that Mars was Earth-like. They found continents, they found oceans, they in fact found canals on Mars. Some people thought there were actually Martians who'd built and engineered canals on the surface of Mars. None of that exists. But the imagination of astronomers was heavily influenced by what they wanted to discover about Mars. And I'm not sure that's changed. We see in Mars a reflection of ourselves because the first thing we knew about Mars was that Mars was Earth-like. But how Earth-like is Mars? That's the question. That's what scientists are now trying to figure out. I want to show you some images of the surface of Mars to try to convince you of just how fascinating and intriguing and mysterious Mars is. This is an image of what is called an outflow channel. And I hope you can see my mouse here. At about 9 o'clock in this image, what you see is what I'll call the headwaters of this outflow channel. In that region, there was a tremendous amount of water that must have been either underground or frozen beneath the surface of Mars. And something happened to catastrophically release that water, and it flowed across the image from left to right in this outflow channel. The amount of water flowing in that channel was enormous. This is a 300-mile long portion of a 1,000-kilometer long outflow channel. The region at the head flows where you see it, that's about 30 kilometers across, 20 miles across. This is a big dump of water. This is another ancient outflow channel. The outflow begins at the bottom of the picture at 6 o'clock, just to the right of the center. The water, again, catastrophically was released and flowed upwards, carved out these channels, flowed around these ancient craters. The amount of water flowing in this outflow channel was almost certainly greater than the amount of water that's carried by the Amazon River today. This is a lot of water. This is an outflow channel called Asuga Valleys, the Asuga Valley. The length of this is 164 kilometers, 100 miles. In some places, it's 20 kilometers wide. It plunges to a depth of almost a kilometer. This is Cerberus Fossae. The water originated, we think, from these cracks that run from about 3 o'clock up toward 12 o'clock. The water would have been released there and flowed downwards towards 7 o'clock in this image. This is another image of an outflow where the water flowed from the top right. The topography is high at the right and lower at the bottom, and the outflow began at the top right and flowed across the screen and then downwards through here. These are all over the ancient surface areas of Mars. This is a region in what's called Hellas Basin, where the outflow channels started at the top. Started at the bottom. I may be reading this wrong. I should read my own figure captions. The water flowed downhill toward the bottom. So the water started up here, was released up here, flowed downwards from 11 o'clock down toward 5 o'clock.
Professor Weintraub, we have a question.
Okay.
How do we know the outflow channel had water as opposed to some other liquid?
Right, that's a great question. Could it have been some other liquid? There has to be enough of that other liquid to make it a possible liquid. The only other thing that could possibly have ever been in liquid form on the surface of Mars, other than lava, and these are not lava flows, would be carbon dioxide. But it's really tough to get carbon dioxide into liquid form. It has to be incredibly cold. The pressure has to be a bit higher. It's very, very unlikely that these flows could have been carbon dioxide. There are a few tiny little flows down a cliff face on Mars. Some of those tiny little flows might have been liquid CO2 flowing for a brief moment, but liquid CO2 couldn't flow for distances of 1,000 kilometers in that volume on the surface of Mars. Flowing lava, and Mars does have ancient volcanoes. Flowing lava leaves different signatures than these kinds of signatures. In this particular outflow, it's what's called sinuous. It's flowing from the bottom right up, and it curves and curves and curves and curves like a Mississippi River. Lava doesn't flow in this kind of way. So it's very, very unlikely that it was anything except water. But that's a good question, which astronomers have been working on, proving the answer to the question that I just gave you for much of the last 30 years. This is an image of something that's very small. This is a rock. This is a slab of rock known as Old Soaker that's been studied by NASA's Curiosity rover. This is a piece of mud with cracks on it. These are the kind of cracks that forms in clay when the rock layers are wet and then dry out. This tells us that not only were there these outflows on the surface of Mars, but there were lakes, there were ponds, there were great basins of water in which eroded dirt flowed in and got compressed on the bottom and formed sedimentary rocks, which grew and cracked in these layers. which this also means that Mars not only had water buried under the surface that could erupt and flow on the surface, but Mars had liquid water on the surface for an extended period of time.
And Professor, we have another question about this.
Go ahead.
Are there any theories as to how long ago the water flows emptied?
Yes. Take a look at this slide. Thank you for that. I must have planted that question, so let me try to answer it with what you're seeing here. This is an ugly looking thing because it's a bunch of numbers, but it's not that hard to understand. The first column tells you these are the names of some outflow channels. The second column tells you when those features had water in them on Mars. So this feature known as the Ravi outflow channel, that's been dated as 3.5 billion years ago. That water didn't flow recently. That was flowing on the Mars surface a long time ago. Most of these features are billions of years old. GY stands for giga years or billions of years. So the Aries channel, 2.5 to 3.5 billion years ago. However, look at this the last one, the Athabasca outflow channel. That one flowed on Mars somewhere between 2 and 30 million years ago. For an astronomer understanding the history of Mars, that's yesterday morning. That's not billions of years ago. That's not hundreds of millions of years ago. That outflow channel flowed fairly recently in Martian history. The other interesting data point on here is this fourth channel. This says minimum estimated GEL. GEL stands for global equivalent layer of water. If you took the water in the Cassini outflow channel, and we estimate how much water that was. If you then spread that water evenly over the entire surface of Mars, pretend Mars doesn't have mountains or valleys, it's just a smooth billiard ball surface. That water would create a global ocean 3.8 meters deep, 10 feet deep. The total estimate for how much water flowed in all of the outflow channels found on Mars is found in the last line here, from 500 to 1,000 meters deep. 1,000 meters would be more than 3,000 feet deep. If you took all the water that's been identified flowing in these channels, you would have an ocean covering all of Mars to a depth of 3,000 feet. And that's a lot of water. But again, in answer to the question that was just asked, most of that water flowed a long time ago. But some of it is probably still there based on outflow channels like the Athabasca channel. This is a contour map of the south pole of Mars. At the very center is the south pole. And if you can read contour maps, you know that's the highest elevation. And then you go down in elevation as you go away from the pole. And you can see all these layers at the pole. These are layers of water ice. The ice caps are mostly water ice. This is an image of the South Pole again, but this was an image created by a radar system on an orbiter that looks down at the surface, sends the radar pings to the surface. The radar penetrates beneath the surface, and this measures how deep the water goes. And you have a chart here, a color bar at the bottom left that tells you that at the very peak up here, the water's 3.5 kilometers thick, the ice. This is all ice. In the green layer, the water's 2.5 to 2 kilometers thick. And all the way down to 75 degrees north latitude, 15 degrees away from the pole, you have water ice layers that are as much as 0.5 kilometer thick, 500,000 feet thick. So there's a good bit of water there. This is an artist's conception of what Mars probably looked like 2 billion years ago. If you took all the water we know about on Mars and spread it out, it actually wouldn't create a global ocean because the northern hemisphere of Mars is low topography, low elevation. The southern hemisphere is much higher elevation. We call it the southern highlands. So the water would pool in the northern hemisphere and create this giant ocean covering most of the northern hemisphere of Mars. If we take the amount of water that we already know exists on Mars, you would get a global ocean that would be 21 meters deep. and then you'd pile it up in the northern hemisphere so it would be deeper. All the words on the right-hand panel is a story I want to quickly lead you through. This is how we've estimated how much water Mars has lost. Water is H2O. Most of you remember and have forgotten your chemistry to know that, but water is H2O. Water can actually also be HDO or D2O. D stands for deuterium rather than hydrogen. Deuterium is just heavy hydrogen. So H2O is heavy water. D2O is even heavier water. If you looked in my cup of tea right now at the water molecules, 1 in every 6,400 hydrogen atoms is actually a deuterium atom, which means 1 in every 3,200 water molecules is H2O, HDO. Planetary scientists think that Mars and Earth formed with the same ratio of deuterium to hydrogen, this 6,400 ratio, which is really 1 to 6,400 would be the deuterium to hydrogen ratio. So when the planets formed, we believe they should have had that same ratio of deuterium to hydrogen, but we've measured the deuterium to hydrogen ratio on Mars today, and it's 8 times greater than on Earth. And the way you take that same ratio, 1 divided by 6,400, and turn it to 1 divided by 80, is you lose the hydrogen atoms to space. You pump the hydrogen atoms into the atmosphere, the water molecules in the atmosphere, ultraviolet light from the sun busts up the molecules into hydrogen atoms and oxygen atoms. The hydrogen atoms are very light and they're lost to space. The oxygen atoms rust the rocks, which is why Mars is so red. Mars has lost most of its water. The deuterium hydrogen ratio is the smoking gun that tells us Mars has lost probably 85% of its original water, which means if we go back 2 billion years, the global ocean on Mars wasn't 21 meters thick, it was 137 meters thick, or about 450 feet thick. And then if you move all the water into the northern hemisphere and make an ocean, it would be even deeper. Mars once had a lot of water, which means Mars might once have looked like this. This is not Mars. This is Shark Bay in Australia. In Shark Bay in Australia has these things that look like rocks, but these are not rocks. These are living things. They're known as stromatolites. They are formed from layer upon layer upon layer of blue-green algae, a kind of bacteria that grows in a mat, almost like coral, and leaves a layer behind it and grows to another layer and leaves a layer behind it and grows and grows and grows and forms these things that look like rocks, stromatolites. Stromatolites are, as best as we know right now, the first life form that we've identified on Earth. The oldest stromatolite fossils are more than 3.5 billion years old. We know life existed on Earth as far back in time as 3.5 billion years ago. And when those stromatolites were first growing on Earth, Mars almost certainly looked just like this. Lots of water, wet on the surface, warm enough to have these oceans on the surface, warm enough that life on Mars was possible. That doesn't mean Mars has life. It means Mars had the conditions long ago to have life just as the Earth did.
Professor, we have a couple questions.
Okay, go ahead.
So it's kind of multiple parts to it. What are the leading theories of what happened to the thousands of feet deep water?
The most likely scenario, which we are pretty certain is right, because we have a spacecraft orbiting Mars called MAVEN, a NASA mission called MAVEN, whose job is to measure the atmosphere. We are pretty certain, with some of the evidence being that deuterium hydrogen ratio I just told you about, that most of the water was lost to space. It's just gone. The water was on the surface, some of it evaporated, and then it was lost, completely lost to the planet. It's gone.
And then we also have a question about tritium and the decay rate of deuterium.
Okay, tritium is an even heavier form of hydrogen. Hydrogen has 1 proton in the nucleus. Deuterium has 1 proton plus 1 neutron in the nucleus. Tritium has 1 proton plus 2 neutrons in the nucleus. So tritium is an even heavier form of hydrogen. Nobody is measuring the tritium abundance on Mars. It's just way too low. It's pretty hard, almost impossible, I would think, to measure. That would be very hard to measure even on the Earth if you had a telescope looking down at the Earth. So no one's paying attention to that. If you could measure that, you probably would get some additional evidence that would tell you about the history of water on Mars. But the focus has been on deuterium rather than tritium.
And the last question is, where is the oxygen?
Where is the oxygen? On Mars, there is oxygen in water molecules, H2O. There's lots and lots of oxygen in carbon dioxide molecules, CO2. There is virtually no oxygen in the form of oxygen. Mars has almost no free oxygen in the atmosphere, no ozone layer. All the oxygen on Mars is bound up in other molecules that include the oxygen, mostly the water and the carbon dioxide. So if we want oxygen on Mars, if you want to go to Mars and breathe, you're going to have to manufacture the oxygen by extracting it from the water, by extracting it from the carbon dioxide. And since you need the water to drink, you're not going to bust up the water. You're probably going to want to bust up the carbon dioxide to manufacture oxygen. The water that's left, by the way, on Mars, 15% of a lot of water is still a lot of water, which means we think there's lots of water left on Mars. We see that in the ice caps. We also see evidence of the remaining water as underground deposits beneath some of the big basins, but we haven't drilled 100 meters into the ground to find that water yet, but we think it's there. Is that all the questions, Isabella?
Yes, for now.
All right, I'll move on then. Given that Mars might once have had life, the question is, what do we know about the possibility of life on Mars? So we're going to change horses here and talk about something different, what I call the dawn of the Mars Methane Era. That began with the launch of this rocket. This was the Mariner 7 spacecraft, which went to Mars in March of 1969. For the most part, people weren't paying attention to this rocket to Mars in 1969 because 3 months later, we landed on the moon. On August 5th, 1969, this flew by Mars. Again, no one was paying attention because the astronauts had just come back from the moon. But this was a spectacular mission. It took a grand total of 126 pictures of Mars, but one of the things it tried to measure was the amount of methane in the Mars atmosphere. And in a moment, I'll tell you why that's important to try to do. The Mariner 7 mission claimed to have detected methane, a tremendous amount of methane. They were wrong. They hadn't detected methane. They had to retract their claim of discovery. They'd actually detected carbon dioxide. But this set in motion the idea that if we could detect methane on Mars, in the atmosphere of Mars, we'd have a spectacular discovery. Why? This is why. This is a cow. Hope you can see my cow. What does a cow do? And a cow eats grass. The grass goes down its esophagus into its stomach, where some bacteria digest and ferment the grass. The cow's happy. Some other bacteria in the cow's stomach convert the hydrogen and the carbon dioxide gas from the fermentation into methane. Those bacteria are known as methanogens. That methane then needs a way out of the cow. And the methane comes out both ends of the cow. Cows are not alone. This is where the methane in the Earth's atmosphere come from. Let me walk you through this pie chart. The top piece up around 11 to 12 o'clock, 10% of all the methane in the Earth's atmosphere comes from rice paddies. 30% comes from landfills, from wetlands, from water treatment facilities, from bacteria that are digesting organic matter and producing methane. 25% comes from the production and the distribution and the use of fossil fuels. All the fossil fuels are ancient life that formed coal and oil and shale. Termites produce about 15% of the methane, and ruminant livestock, my cow, sheep, llama, goats, they produce the other 20%. 100% of the methane in the Earth's atmosphere is produced by life. And the methane can't survive for very long in the Earth's atmosphere. If you turned off all of these processes tomorrow morning, produced no more methane, in about 12 years, the methane would be gone. Ultraviolet light destroys it. Other chemical reactions in the Earth's atmosphere destroy it. The methane can't survive in an atmosphere as rich in oxygen as the Earth's atmosphere. If you could go to the other side of the Milky Way galaxy, 100,000 light years from the Earth, and point a telescope at the Earth, you would have no trouble proving that life exists on the Earth, because oxygen and methane cannot coexist at the levels they exist in the Earth's atmosphere. The only way to have them both is for an organic process, life, to be producing. Methane, if there is enough of it, is proof that life exists. There's nothing else we can imagine that could produce this. On Mars, if there is methane, big if there's methane, its lifetime is about 300 years. If there's methane in the atmosphere of Mars, it did not start there 4 billion years ago. It wasn't there 2 billion years ago. It wasn't there 1,000 years ago. Any methane in the atmosphere of Mars was produced yesterday, last year, a decade ago. It is being actively produced and injected into the atmosphere of Mars. That's why we're searching for methane. It would be an incredible proof that life exists now on Mars if there's enough methane. The question is how much methane. Mariner 7 thought it found a lot of methane. They were wrong. Other people made observations in the 1970s, the 1980s, the 1990s, the 2000s. Most of those observations have been refuted. Some of those detections are controversial at best, and to solve the mystery of where the methane comes from, we went looking for it. Now, I want to tell you, this is a cartoon I'm going to come back to. This is a cartoon of possible sources of methane. It's busy, but you can handle this. Dust rains down onto the surface of Mars from comets, from asteroids, from meteorites. Those deposit carbon-rich material on the surface. Ultraviolet light could interact with those surface organic molecules and produce methane. A second possibility, there could be formaldehyde and methanol in the soil of Mars. That could react with carbon dioxide in the atmosphere if it's stirred up by dust devils, and that could produce methane in the atmosphere. Mars has all these materials. The bottom right, you have a piece of olivine rock. That's rock that comes from volcanic processes. We know Mars has lots of olivine. Water reacting with olivine produces methane. It also produces a rock called serpentine, so the process is known as serpentinization, fancy word for you. That would be an underground production process for methane, and then the methane would outgas, hiccup out of the ground. And the fourth mechanism would be methanogenic bacteria, microbes under the surface that manufacture the methane. And again, the methane would grow in pockets of gas under the surface and erupt out of the surface. What are we doing to try to explore these possibilities? We sent a chemical lab to Mars. The Curiosity rover, which landed on Mars in 2012, is a roving chemical laboratory. It's like taking your chemistry lab and taking it to Mars. This is a wonderful self-portrait of the rover. The camera sticking up to the top of the rover looked all around, and they took about 1,000 images and then put them all together to make this composite selfie. This is the most expensive selfie ever taken. Curiosity rover spent its first year trying to measure how much methane is on Mars, and the answer was probably none. The measurement was less than 1/5 of a part per billion in the atmosphere, which means if you have 5 billion molecules in your hand from the atmosphere, maybe one of them is methane. One methane molecule in 5 billion, that could be produced by processes that don't involve life. The Curiosity rover kept working, and 2 years later, they reported an updated measurement, and the updated answer was Mars doesn't have methane very often, but they detected a hiccup in early 2014 in which the amount of methane went up to as much as 7 parts per billion. Now, that's not a lot of methane, but it's a whole lot more than what we call the background level. The background level is a couple of tenths of a part per billion. That's just in the noise. And then, boom, you get a hiccup of 7 parts per billion, and then it disappeared. Now, remember, the lifetime of methane on Mars should be 300 years. If this methane is evenly distributed around the surface, it should last for 300 years. But it wasn't there in 2013. It was there in January and February of 2014, and then it was gone. Which means it's not a global atmospheric layer of methane. It was just a little bubble of methane that probably, if it's right, came out of the surface, floated over the rover, and then dispersed until it was undetectable. That's how we have to explain that detection, if the detection is right. A few years later, the rover team released their newest results on their methane measurements, and they didn't detect any big hiccups after the first one, but they did detect what they called seasonal variations, in which the amount of methane went all the way up to 0.7 parts per billion. Not high, but there seemed to be seasonal fluctuations in methane. Then, last year, almost a year and a half ago, the Curiosity rover measured the largest, highest amount of methane gas they'd ever measured, 21 parts per billion. That is a big hiccup. 2 days later, that number was down to less than 1 part per billion, which either means the Curiosity rover made a mistake, or it means there was a big hiccup, and a plume of methane came out of the ground, floated over the rover, and then dispersed.
Professor Weintraub, we have a question.
Right.
Why is there methane on Titan if it so easily disintegrates?
Good question. Titan is a moon of Saturn. Titan's atmosphere is very rich in methane. Titan's atmosphere, however, is what we call a hydrogen-rich atmosphere. A chemist would call it a reducing atmosphere. It's not an oxygen-rich atmosphere. In oxygen-rich atmospheres, methane can't survive. The oxygen wins and destroys the methane. In a hydrogen-rich atmosphere, methane is CH4, carbon with 4 hydrogens bound to the carbon. That's a hydrogen-rich molecule. And in an atmosphere that has lots of hydrogen-rich materials like ammonia, which is NH3, or water, which is H2, that's also a hydrogen-rich molecule, the methane can survive. The planets Uranus and Neptune also have hydrogen-rich atmospheres in which methane can survive. So there are places where methane can survive forever, but those have to be chemically active environments in which the chemistry does not destroy the methane. An oxygen-rich environment like Mars's atmosphere and like Earth's atmosphere will destroy the methane. The most important molecule in Mars's atmosphere is carbon dioxide. There's no hydrogen in carbon dioxide, so the methane gets destroyed. That's a good question. All right, back to Mars with the Curiosity rover. The best interpretation is there were these plumes that hiccuped out of Mars and floated over and then were gone. The last important measurement from Curiosity is that they saw these seasonal variations, and you don't need to understand much here, but if you look at the bottom right plot, you just see the amount of methane goes up and then goes down. It's most abundant in northern summer, and it's then goes down in northern autumn and northern winter, and then maybe back up again. Have they seen it go back up again in year 2? I haven't seen the data for that yet. They haven't released the data for that yet. But a seasonal cycle would be very hard to explain using the ultraviolet surface organic process or this process of dust devils. Those shouldn't produce seasonal variations, which means we're down to 2 possible sources of the methane. We need methane produced underground that hiccups out of the surface, which means either there's a lot of methane produced from serpentinization or there's bacteria under the surface. We're narrowing it down, and it's getting incredibly interesting. I want to take you somewhere else, not to Titan, but to some other moons in the solar system to finish up this conversation. Europa is a moon of Jupiter. No methane there. But Europa has an icy surface which is warm and smooth. Beneath the surface of Europa is a global ocean. We're absolutely certain of that. The surface of Europa is 10 to 100 kilometers thick of solid ice. But as you go into Europa, you eventually get to a layer, a depth at which that water ice is warm, and there is an ocean that is a global ocean surrounding every part of Europa, but it's underground. It's warm, it's wet, it's got carbon, nitrogen, oxygen, molybdenum, magnesium, calcium. All the ingredients for life exist in that subsurface ocean on Europa. This is Enceladus, a moon of Saturn. Enceladus is like Europa. The surface is solid water ice, and beneath the surface is a global ocean of warm liquid water. This cartoon shows you what we think those moons look like with the icy crust, the subsurface ocean of water, beneath that hot rock which heats the water from below and pumps heat into that ocean and keeps it warm. This is an actual image of water geysers erupting off the surface of Enceladus, 100 miles up into space. We know there is water, liquid water, warm ocean water beneath the surfaces of these two moons. NASA had a mission that went to Jupiter called the Galileo Mission that operated from 1995 to 2003. And in 2003, we knew about Europa's ocean, its subsurface ocean. And the Galileo mission was running out of fuel. And astronomers became worried that the mission might crash accidentally into the surface of Europa and contaminate Europa. And the decision was made that we should not allow that to happen. So the last little bit of propellant was used to steer the Galileo mission into Jupiter and have it crash into the atmosphere of Jupiter and burn up so that it could never contaminate Europa. The Cassini mission went to Saturn and orbited and studied Saturn and the rings and the moons of Saturn for 14 years, from 2004 to 2017. And you know what's coming. At the end of its mission, when it was almost out of propellant, NASA made the same decision. Take the last little bit of rocket fuel and steer Cassini into the atmosphere of Saturn and burn it up so that it could never, ever, a million years from now, 20 million years from now, it could never crash into the surface of Enceladus because we don't want to contaminate a world that might have life. This is a report from just a couple years ago from a global team that is searching for evidence of life deep beneath the surface of the Earth. And they have found it. This is a nematode, a little worm guy that lives a mile, 1.4 kilometers beneath the surface of the Earth. They have found what they call a subterranean biosphere. This isn't life in the deep oceans. This is life beneath the rock. They have found life a kilometer deep below the floor of the ocean. This is life that exists independent of the sun. The energy for this life comes from inside the Earth. It's a warm, wet environment, heat from within, energy from within. They suggest that 70% of Earth's bacteria and what are called archaea exist in this subsurface. The deepest organism found was found 2.5 kilometers beneath the surface. Life exists in these deep underground environments on the Earth. Could life exist in these deep underground environments on Mars? We're keeping our hands off of Europa. We're keeping our hands off of Enceladus because life could exist there. And Mars is the closest place in the universe where life beyond the Earth could exist. And we're looking for evidence of that life. And yet we're not doing what we did with Europa and Enceladus. We're planning to send people with all their pollution to Mars. The question is, should we do that? Do we have the right to do that? And I will stop there.
Oh, sorry, go ahead.
I'd say I'll stop there and let people contemplate that idea, and I'll be happy to take some questions.
So we did have a question just come into the chat asking, Panspermia, is there a chance that Earth's life forms originated in Mars?
That's a great question. Panspermia is the idea that life could start on one planet and spread to another planet. And the answer is yes, that's possible. Life could have started on Mars, and an asteroid could have smashed into the surface of Mars, kicked off some debris. That debris goes off into space, and eventually one of those rocks lands on Earth and deposits Martian bacteria on the Earth. A very good possibility is that we are descended from Martians if life exists on Mars. It's more likely that life could go from Mars to Earth than Earth to Mars. So your grandparents, metaphorically speaking, could actually have been Martians if we detected life on Mars. And if that life was DNA based, it's hard to imagine that DNA based life would have formed independently on two different planets this close together, which almost certainly means life started on one of those worlds and was spawned to the other world. Now, of course, we don't know if Mars has life yet. We don't know if that life, if it exists, is DNA based, but there is the potential to actually test that question of panspermia. Another question, Isabella?
No, we don't have any questions. If anyone has anything, please drop them in the chat so we can get the answers to your questions. But right now, that's it.
I do think, to continue with that last answer, discovering life on Mars, if there's life on Mars, would be one of the most incredible discoveries ever made. It would teach us whether life exists in abundance in the universe. If we discovered life on Mars, that tells us that life can exist on other worlds. If we discover life on Mars that is not DNA based, and keep in mind every last bit of life on Earth, from the COVID virus to the bacteria in these subsurface reservoirs to elephants and giraffes, were all DNA based, DNA and RNA. We all came from the same beginning. If life on Mars exists and it is not DNA based, that means two different ways of getting life started happened on two different planets orbiting a run-of-the-mill star in a run-of-the-mill part of a run-of-the-mill galaxy. And it probably tells us life is very, very abundant in the universe.
So we have a comment and a question. The comment is, so if that's true, then our ancestors would tell Elon Musk, you're going the wrong way.
Probably, yes.
And then we have a couple questions. Any amino acids found on asteroids?
We have not visited asteroids yet to find or search for amino acids, but in certain meteorites, a handful of meteorites, so rocks that came from asteroids and fell to the Earth, yes, amino acids have been found. The most famous one is called the Murchison meteorite. It fell in Australia in, I think, 1969. 1973 or thereabouts. There's another one that fell in Mexico in 1969. That's the Allende meteorite. Those two meteorites both have amino acids. Many dozens of amino acids have been found in those meteorites. Several of those amino acids are the same ones that are found in you. They also have found the basic nucleotide building blocks of DNA in those meteorites: uracil, guanine, cytosine, I forget what the fourth one is. But those have all been found in a handful of meteorites. Okay. But not yet on asteroids.
Is the water on Mars drinkable for humans? If not, is there a known process or theory to make it drinkable for humans?
Is the water on Mars drinkable? Water's water. H2O is H2O. So if it's H2O, you can drink it. If it's H2O with contaminants in it, you might want to be careful. Now, the H2O on Mars could be contaminated with Martian equivalents of bacteria. And if those bacteria would be harmful to you and me, then you probably don't want to drink that water without sterilizing it. There are also places with water on the Earth where we've polluted the water, so they have heavy metals in them, which you don't want to drink. It's possible that those same heavy metals could exist in some of the water sources on Mars. So once you find the water, you're going to want to make some careful measurements of what other materials may be in the water. But water itself is water. You could drink water if it's pure water, no problem.
Other than methane remnants, how do we find it on Mars? Crash a probe into deeper soils, drill, how?
I assume that's how do we find life on Mars if it's there.
I think so, yeah.
The methane's an easy way to look for it because it's just out there in the atmosphere. Drilling for it would be a good way to go, and the rover spacecraft, the Mars 2020 rover that will land in February, has a drill bit on it, which will drill down about 6 meters, about 20 feet. And if there is bacteria 20 feet below the surface, we may well find it with that mission. The 2020 rover also has a task. That task is to wander around, find rocks that look like they might be rocks that could have fossils or evidence of life, collect them and pile them up. And in a few years, we'll send another small mission to Mars to land there, pick up the pile of rocks and bring them home. So then we'll have some Martian rocks to actually test in Earth laboratories to look for things like amino acids. What else could we do if you actually either put footprints on Mars, had astronauts on Mars, or had artificially intelligent robotic rovers on Mars, or even be more imaginative, little dragonfly robots that can fly around? You could find caves. You could go into caves, explore inside the caves, look for evidence of life in different ways in the caves. There are a lot of people trying to think about how we might look for evidence of life. There are no giraffes on the surface of Mars. What Carl Sagan is famous for having described as macroscopic life, there's no macroscopic life on Mars. Any life on Mars is microscopic life beneath the surface. But if life existed there 3 billion years ago, it could have found a way to survive for 3 billion years beneath the surface. The surface is hostile. The surface is irradiated with ultraviolet light from space, with X-rays from space, with what are called cosmic ray particles. Without protection, you would die on the surface of Mars. And in fact, the astronauts that go to Mars at the moment, they couldn't live on the surface of Mars without a layer of lead to protect them. So they would have to either take a habitat with them that could shield them from the bad stuff from space, or they'd have to find a cave to live in. So any Martian life, if it's there, has to be beneath the surface. So you need to find a way to explore beneath the surface by drilling or by finding caves and wandering into the caves.
And I think our last question, are you concerned we are contaminating Mars with life?
Yes. I maybe should stop with a short yes, but yes. NASA tries very hard to decontaminate, to sterilize spacecraft that go to places like Mars, but we can't sterilize them completely. And we know we have already sent bacteria to Mars on these rovers. Now, the bacteria we've already sent to Mars probably has not contaminated Mars in a significant way because it's inside the rover. And if it gets out of the rover, it's going to be sterilized by the ultraviolet light and the X-rays. So we probably have not contaminated Mars yet. But if we send astronauts to Mars with all the life support systems and the waste they produce and the accidents that will happen when we send humans to Mars, that's when we'll contaminate Mars.
Great. Thank you so much, Professor Weintraub. We really appreciate it. Thank you everyone for participating, the great questions, and please take a couple of minutes to answer the survey that Catherine dropped in the chat box. And I think that's it for tonight. Thank you so much.
Thank you, everybody, for spending some time with us.
Thank you, everybody.